We are with waves. This is the first of 5, I think, probably extended out to that, might go to 6. Who knows? Let's see where it takes us. You've already seen this. This is the animation of something we've already looked at in the electron. The electrons are jumping off the surface of this hot cathode by a process called thermionic emission, and then they're striking the anode, which is the thing which is shaped like a wedge, on the other side. And one electron is producing one photon, and if you've a high enough energy field between the two of them, you high enough voltage between the cathode and the anode, you can produce X-rays, which, as we know, very useful. Must be done in a vacuum. The blue kind of circle thing you see there is a vacuum tube, and the green surrounding it is lead shielding to stop us all dying. So what's next? You have to think about waves. Now, you can stare at this for as long as you want. It's sort of like very calming, I think, especially as at the moment I'm recording this, we can't allow to go to the sea. If you look more at the blue dots, you're seeing a wave. You understand that's a wave. But if you look at the blue dots, you see the blue dot doesn't have a net movement. It's rotating, it's vibrating, whichever you want to call it, oscillating, but it's not having a net movement. The energy, the information, passes from left to right. But the individual dots don't. They stay in the same approximate position. And that's what makes something a wave. So let's start with some definitions. Amplitude, as you can see, is the distance between the middle line and the peak, or the middle line and the trough, of a standard wave. There you are. That bit of the wave is called the crest. That bit's called the trough at the bottom. Wavelength, given by lambda, that's in the brackets there, lambda looks a little like a giraffe, is a Greek letter, is the distance from the equivalent parts of waves. So from peak to peak is where we normally measure wavelength, though you can measure from middle to middle. And the frequency is the number of times it goes up and down a second, which can either be written as per second, but more correctly as hertz. So 50 hertz goes up and down 50 times a second, literally goes from peak to peak 50 times in a second. Okay, now we come into the meat of it. What is a transverse wave? Now, most waves we're going to deal with the transverse. Their motion is at 90 degrees to their direction of propagation. You see, the motion of the individual particles, the motion of the wave, the oscillation of the wave. So, transverse waves are when the displacement is at right angles to the direction of the wave. So the oscillation or the displacement is at right angles. Whereas a longitudinal wave, it's a long word, you're going to have to learn. That's in the same direction of the wave. And you can see there's a helpful little red line placed on the left-hand side showing how these waves are formed. Essentially, these are constrictions in the air. There has to be a medium involved because this is indeed sound. We're talking about sound wave. So the top one is light waves and the bottom is sound waves. God almighty, can I turn that off? Let's try and turn off that. Hey, there we go. We're all on a learning curve here. Let's hope that doesn't make any more noise. I hope I haven't muted the microphone. I'll only find out at the end, I guess. Okay, so light is the top one, is a transverse wave. All electromagnetic waves are essentially the same thing. They're all transverse. They're all things which are disturbing the electromagnetic fields. So light, X-rays, radio waves, infrared, microwaves are all versions of the same thing. The only difference between all of them is how long they are, the distance between their peaks. Longitudinal waves are more or less sound. There's also mechanical waves which are outside, which are still the same sort of wave, but you're outside audible, but are essentially still the same thing. So to look at a longitudinal wave, here is the wave, a very helpful diagram this, where you can see the wave travel from left to right. See, individual particles don't travel, they oscillate, and there's two individual particles highlighted. And the wave travels. That's a wave crest that's being tracked by the word wave. Thanks, Dan Russell. Dan Russell's been making these for an awful long time. The first one was Dan Russell from 16 years previously. So this is a very good little thing. Now, he's also showed what these things are called. Where they're all squeezed together, that's called a compression. which is understandable enough. Now, the new word for in between is called a rarefaction. It's not mentioned specifically on the course, so perhaps we don't have to worry about it, but it's where there's slightly less molecules, usually air molecules, of course, if we're talking about sound. Here's another version of it. You can see a loudspeaker, which is compressing the air on the right. And as it is, you can see the compression. Now, you compare the compression of air, this is the second one down, to the top one, which is transverse, where the compression is up and down. You see, the movement is up and down. But the loudspeaker, which you can see the paper cone is going in and out, the paper cone is pushing the air together, causing these compressions, and then pulling the air apart, causing the gaps, which are called rarefactions. So a transverse wave's oscillation at 90 degrees is the direction of propagation, whereas a longitudinal wave's the oscillation is parallel to the direction of propagation. Now that's quite difficult, it's very hard to remember, and also not incredibly useful. So we need another way of distinguishing between these two waves, and the way is polarization. You see, only electromagnetic waves, which are transverse, can be polarized. And polarization is where you take an electromagnetic wave and you reduce it to one plane of oscillation. So normally they're traveling in all planes at the same time. Now, I can't demonstrate this to my fingers, but basically they're traveling in all angles as they come towards you. So all angles towards you. And polarization reduces them to only one plane of oscillation. So polarization is when an electromagnetic wave or transverse wave vibrates in only one plane of oscillation. Sound, being a longitudinal wave, cannot be polarized. It doesn't travel in the same way. It cannot be polarized. So what's the difference between a transverse and a longitudinal wave? The transverse wave can be polarized and the longitudinal wave cannot be polarized. And that's an easier way to distinguish between the two waves. Of course, the other wave, the brain waves, things like that, they're all just like jokes that I have to have a visual contact with you to do. And it's wasted here. Wasted. Another version of polarization, I think this is a very helpful diagram. Personally, if you look at the left, the light's coming in. That's an unpolarized light. It looks like several egg beaters put together because it's oscillating in lots of different directions at the same time. But all the other directions can't get through that polarizer, which is called polarizer 1, the vertical one. So it reduces to one polarized area. And that one polarized area is polarized light. You see, it's only oscillating in what we call one plane. And a plane is something flat. So transverse waves are plane polarized if the vibration stays in one plane of oscillation, and longitudinal waves cannot be polarized. You might think this is important since I mentioned it 4 times now and had 3 different slides on it. Okay, that's a polarizer actually working. That's a piece of Polaroid. The red light is laser light, which is by definition polarized. So as the thing spins, when it's lined up with a polarization, light goes through. When it's at 90 degrees to the direction of polarization of the light, it cuts the light out. So that's how you can tell something's polarized as well, by rotating a polarized filter in the light. If it blocks out and comes back, then it's polarized light. Yet another diagram. This one's quite a good one as well. You see the 2 torches at the top produce unpolarized light. It hits the first filter and gets polarized. Now, on the left-hand side, the second filter is exactly the same polarization. They're both polarized vertically. So the light goes through because it's already been polarized, so it can pass through a second filter. On the right, however, the second filter, as you can see, has been turned horizontal. And because it's horizontal, it will not allow light polarized vertically through. So what you get afterwards is darkness. And I really need to be there to show you this experiment. Now, some people think of it as this rope and the gate. I never found it very useful, but if you find it useful, it's there for you. You can see that the rope can oscillate through the gates because they're both vertical, but the second one is actually horizontal, so the rope can't oscillate through it, apparently. Okay, so filters are actually made up of carbon chain molecules. They're very simple devices, simply cleverly laid down carbon chain molecules, usually done electrically, so they're all lined up, because when they're all lined up, they won't block the light going through, But if you turn it the other way around, they're lined up with the light and they can block it. It's just as simple as that, really. They're just these long carbon chains, hydrocarbons. Actually, you know, like alkanes and things like that. Okay, so what do you use a polarization for? Well, use it for finding faults or stress points in clear plastic models by shining polarized light at them and seeing where there's interference. You can send two signals to the same aerial at the same time, and the two signals don't interfere with each other because they're one's polarized vertically, the other horizontally. That used to be easier to explain when we had television aerials on the roof. They were all either straight up or flat, and the two of them would receive two different signals, which was like, you know, very easy to do, and you could squeeze an awful lot more signals into the same waveband. Now digitally we, you know, greatly surpass what we can do with that. So, you know, that's one, two signals. And the last one, the most interesting one, is 3D images. Because if you're looking at a 3D image or an unpolarized thing, what you're looking at is polarized light. And polarized glasses will actually reduce glare, and also they can be made for 3D films. So here's an example of polarized glasses reducing glare, because glare tends to be polarized light. Like if light shines off of snow or light shines off of a swimming pool, both water after all, the light is mostly polarized. So if you wear polarizing glasses, you stop the light, the vast majority of the light coming into your eyes without, you know, not being able to see. So polarized glasses will reduce that. Okay, so now my favourite bit here, I get to sing. Right, yeah. What's a quiet low frequency sound? Looks like that. This is quiet, so it has a small amplitude. Low frequency, the peaks are far apart. Whereas a quiet high frequency sound, the peaks are close together. That's high frequency but low amplitude. So quiet, high frequency, a low wavelength, small wavelength. If you have a loud sound with a low frequency, you increase the amplitude. You don't necessarily, well, you don't increase the wavelength. And a high frequency sound is that one. So the first one, quiet sound, low frequency. Next one, quiet sound, high frequency. Then you've got loud sound, low frequency. Then you've got loud sound, high frequency. Yeah, that last one's a bit painful even for me. I'm sure for you, it probably, you know, indescribably unpleasant. Okay, then we have equations. Yes, it's physics. It's maths. Come on. The speed of a wave is always its frequency times its wavelength. One of the most useful equations in all of physics, and certainly to you because it comes up all the time. 4 different questions. Yes, there's a triangle involved if you're into triangles. So frequency is actually equal to the speed of the light divided by the wavelength. It's just a manipulation of the previous formula. The previous formula was the 2 and multiplied. Speed of light was frequency times wavelength. Here we have frequency as c over wavelength. Now this is very important. We have to convert wavelength to frequency quite a lot in physics, and even more perhaps in leaving cert physics. So you use this formula, you convert any wavelength to frequency. So remember, frequency, how many times something past the point goes up and down in a second, and it's measured in hertz. Wavelength is measured in meters, and the speed of light is meters per second. And now we have some questions, and I'm going to just, ask you very quickly to do this. Water wave has a frequency of 2 hertz and a wavelength of 0.3. Now remember, what we're talking about is we multiply the 2 of them together to get the speed of the wave, okay? So if you multiply the 2 together, you get 0.6 of a meter per second. It's as simple as that. A water wave travels at 1 and has a frequency of 5 hertz. Well, the wavelength is always the speed divided by the frequency. Well, 1 divided by 5, 0.2. So it's 0.2 of a meter. The speed of the sound is 330 meters per second. That's about right. When Dave, good old Dave, when Dave hears this sound, the ear vibrates 660 times a second. Dave's amazing, isn't he, if he knows that? If he can count them. That's quite quick. He probably is one of these perfect pitch people. What is the wavelength of the sound? Again, we divide. We take the 600 and we divide it into the 330. 660 divided by 330. That doesn't take a genius to work out. It's half a meter. So the wavelength is half a meter. Right, this one you can do in your head. Purple light has a wavelength of 6 times 10 to the minus 7 meters and a frequency of 5 times 10 to the 14 hertz. What's the speed of purple light? Come on, you can do this in your head. Because the speed of light's always the same. 3 times 10 to the 8. Come on, wake up, smell the coffee. Refraction. We've done this, yes, in light, remember? Where light bends. But this is the change of speed. And what's actually happening is as it moves into the denser medium, it slows down and then speeds up when it leaves again, which still happens when it's travelling straight, but you can't see that slowdown because, well, it's slowed down from something very, very quick to something very almost as quick. So, and this gives all these various things, you know, the refraction, dispersion of light. Now, the reason light disperses is because the different frequencies bend or refract by different amounts. And that's why light disperses into its colours. You know, the lunatic is on the, you know, the lunatic is on... It's dark side of the moon. Why don't you just have a little go at reading this and trying to put in the words. Okay, let's do the words, shall we? Refraction is when waves speed up or slow down due to the travelling in different media. A media is something that waves will travel through. In the case of light rays, they are slowed down by the water and are bent. That's it, causing the ruler to look odd. The two mediums in this are, well, they are water and air, or air and water. But remember, what's actually happening is the wavelength is changing to change the speed. The frequency stays the same, which is why the colour is the same, because our eyes respond to colour. Well, this is a jolly little diagram. I quite like this diagram. You can see light heading from a less dense medium to a more dense medium. Air to water, if you like, or air to glass. And what you're seeing is that the wavefronts are closer together in the glass. I'm going to say glass. Water's as good. They're closer together because, of course, they've slowed down. So the frequency is the same, as I was saying. There was no change in the frequency. The colour appears the same to our eye. But the wavelength is quite different. The wavelength is reduced. So the wavelength has to change because the speed has changed. They're proportional to each other. So why has it actually changed direction? Well, as you can see, as the wavefronts actually change direction, they stay together. That's the most important part. The wavefronts can't break apart because they've always got to travel connected. The only way they can stay connected when one half of them has changed and the other hasn't is by changing direction. So the change in direction is due to the fact that it has greatly slowed down. So, reflection, that's reflection just bouncing off. Refraction, yeah, it slows. There you are. See, look, they get closer together, which if we pass it through an angle means that they'll bend, you know, that's the bend. But we also have something called diffraction we'll talk about later, which is when waves spread out. They spread out when they go past an obstacle. Okay, this would be your homework, and that would be the end of this section. I hope some of that made sense. I'll have to edit it a bit.